welcome to this explainer. Today, we are diving straight into the invisible, microscopic world of molecular engineering. We're going to trace its path all the way up to some truly futuristic, extreme survival gear. Specifically, we're exploring the molecular architecture of heat and unpacking something called phase change materials, or PCMs. It's a fascinating journey into how scientists are literally weaving the future of temperature control right into the threads we wear. Let's get into it.
You know that incredibly frustrating paradox, right? You throw on a heavy winter coat, step outside, start walking really fast, and within minutes, you're sweating. But the moment you stop moving, that trapped moisture inside your totally passive traditional insulation cools down rapidly. Suddenly, your heavy winter coat is actually making you freeze. In extreme environments, this is a highly dangerous phenomenon known as the afterchill effect. The problem is that traditional fabrics just trap heat. They are completely passive. They do not adapt to your body's changing needs.
To understand why this is actually a huge deal, we need to talk about biological homeostasis. Basically, this is your body's constant, exhausting battle to maintain a stable internal core temperature of roughly 36.5 degrees Celsius. When you're in extreme cold, your body's internal mechanisms simply can't replenish the heat lost to the surrounding environment fast enough. And the stakes here are incredibly high. We aren't just talking about feeling a little chilly. Even a slight drop in your core temperature immediately begins to impair brain function, cloud your judgment, and genuinely threaten your survival. Our bodies desperately need an external, intelligent bridge to help maintain this homeostasis.
Section 1. Architecture of latent heat. So, to fix this dangerous afterchill, we're shifting away from traditional insulation and looking at phase change materials. Think of these as invisible thermal batteries embedded right into your clothing. The molecular selection here is absolutely brilliant. Scientists are specifically using linear hydrocarbons, which are actually byproducts of oil refining. What's amazing is that the melting and crystallization points of specific materials, like N-octadecane and N-icosine, sit right between 25 and 36 degrees Celsius. That perfectly brackets normal human skin temperature, which hovers around 33.4 degrees. It's completely by design. When your skin gets too hot, these materials melt, absorbing your excess heat. And when you cool down, they crystallize back into a solid, releasing that stored heat right back to you. It mimics your internal regulation flawlessly. And the sheer capacity of these thermal batteries is mind-blowing. 245.6 joules per gram. That is the massive amount of energy, known as latent heat, that a material like N-octadecane can store and release during its transition from solid to liquid. To put that into perspective, normal textiles only absorb about 1 joule per gram for every degree they heat up. So PCMs offer a staggering leap in thermal capacity, and they do it without adding any massive weight or bulk to the garment.
Section 2. Engineering the micro-bottle. Now, knowing the chemistry is great, but applying it to clothing brings up a massive engineering headache known as the flexibility paradox. It's a huge catch-22. On one hand, if you just slap solid phase change materials onto fabric, it becomes totally rigid. You essentially create a stiff, bulky armor that limits all your movement. But on the other hand, when those PCMs actually do their job and melt into a liquid to absorb your heat, well, they leak. They stain the fabric, they evaporate, and they permanently lose their thermal capabilities. So we somehow need a way to trap a liquid right inside a piece of clothing without turning it into a rigid shell. The really elegant solution here is a chemical process called interfacial polymerization. It works like this. First, scientists create an oil and water microemulsion that actually contains the liquid PCM. Next, these tiny things called emulsifier micelles rush in and completely surround the oil droplets. Finally, durable shell materials like melamine formaldehyde or polyurea synthesize right at that boundary to form a permanent microscopic shell. Basically, we've engineered a micro-bottle. It permanently seals that liquid energy inside a micrometer-sized sphere. It's tough enough to survive a spin cycle in the washing machine, but tiny enough that the fabric itself stays perfectly soft and flexible.
Section 3. From passive to active. This is where we shift from dumb, passive fabrics to highly active, smart textiles. Engineers are literally giving clothing a nervous system by weaving conductive polymer matrices directly into the fabric. By using electroconductive polymers like PEDOT, PSS, a simple thread is transformed into an interactive sensing interface. Think about what this actually enables. We get real-time active sensing of your skin temperature and hydration levels. We can trigger joule heating, which uses incredibly low voltage to actively generate warmth right through the fabric.
They can even engineer artificial sweat glands that actively perspire to cool you down when you're working hard. It's literally sci-fi technology woven into reality.
Section 4. Precision core sheath spinning.
So how do you actually manufacture a smart thread? If we look at the loom of the future, we see a fascinating process called coaxial electrospinning. Instead of a single solid thread, imagine spinning ultra-fine nanothreads that resemble microscopic coaxial cables. The phase change material, that thermal battery, is safely encapsulated right inside the inner core. It's completely protected by the functional outer sheath, which can be made from all sorts of biocompatible, conductive, or even photoresponsive materials. You get the incredible thermal storage of the PCM, but you never sacrifice the natural integrity or feel of the fiber.
And what about adding the electronics, the actual conductive circuits? Well, there's another massive hurdle there: heat. Printing traditional circuits requires intense heat to sinter or fuse the metals. If you tried that on fabric, it would instantly melt these delicate natural fibers. The big breakthrough here is the use of sinter-free nano inks like gold polythiophene hybrid nanoparticle inks. These allow engineers to inkjet or 3D print flexible electronics directly onto delicate textiles at room temperature. There's no melting, no damage, just a perfectly integrated smart circuit on a piece of soft fabric.
Section 5. Surviving the extremes. So, zooming out to the human scale, what's the ultimate payoff for all this brilliant microscopic engineering? It's the total redefinition of human endurance. By maintaining a dynamic, completely stable microclimate right between the skin and the fabric, we can prevent both lethal hypothermia and that dangerous afterchill effect. This technology is actively replacing those heavy, super cumbersome liquid cooling garments used in space programs. It's protecting military personnel deployed out on harsh glaciers, it's sustaining Arctic explorers, and it's drastically enhancing the daily safety of firefighters and cold storage workers who transition between extreme temperature zones constantly. It saves lives, and it entirely replaces clunky, heavy gear. There's a great quote from researchers at Hsinchu University that really perfectly sums up the evolution we've been tracking today. They note, this multi-core and shell structure enables synergistic cooperation between its various components and delivers on-demand thermal regulation. We've entirely moved beyond just a simple piece of cloth. We are now looking at tri-mode fabrics that seamlessly combine phase-change energy storage, solar absorption, and electrothermal heating into a single cohesive wearable garment.
Which leaves us with a truly exciting prospect. We are rapidly moving toward a future of adaptive nanomaterials, fabrics that can dynamically tune their own infrared emissivity on demand to retain heat or vent it out. So the question I want to leave you with today is this: when our clothes can dynamically tune out the cold universe itself, what extreme environments will we conquer next? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.